So the next topic we're talking about will be principal component analysis, and it is a method to help us to perform dimension reduction. Okay, so what is dimension reduction? When we collect data, okay, usually we will try to collect as many features as possible, right? To collect those data, but there's some data which is useless. As we mentioned before, usually we have an average value. We can calculate the average value right here. We can calculate the variance, okay, right here. So if a feature which its variance is 0, that means all the data, okay, in this feature, okay, this feature would be the same, so that the variance will be 0. For example, we collect the hair color of the students in this class. Okay, if they are all black, that means we cannot differentiate those data point by using this column. So this column is useless because they are all the same, and the reason and the variance value is 0. So when you collect data, if the variance is small, that means it might not be useful to differentiate those data points. So that is one of the reasons. The other is that if two features, okay, if they have a very strong relationship, for example, you collect the height of students, and that is in centimeter, and that is in meters. So we know that they're related, right? Right. 100 centimeters equals to 1 meter. Okay, 1.2, something like that. So if it's possible to help us to to do some kind of preprocessing to remove useless data. So that is called that is what the reason why we want to perform dimension reduction. Okay, so here again we have example, average example. We have 4 different features right here, right? Uh, uh, know that for dimension reduction, it is we don't need target value. We can use x. Simply just use x to perform dimension reduction. Okay. So here we have we have interactable sorry, let me execute it. Okay, so you can see that um, you can interact with this figure. Okay, so you can see that that is the 3D plot of iris data. You can see we have 3 different cluster, right? Usually when we observe this data, okay, like this way, okay, like this, okay, the x-axis is the petal length, the y-axis the petal width, and the z, okay, axis is the sepal length. Okay, we use 3 dimensions to describe the data. Okay, but as you can see, we can turn, we can rotate those we can rotate this data to get a better view to observe the data, right? So I think this one would be better because we can differentiate the green points and the red points better in this angle. For example, right, this one. Okay, so when we perform principal component analysis, it's very similar to for us to rotate the viewpoint, to change the viewpoint. We in order to get the better angle to observe the data. So when we rotate the data, what is the best rotation of viewing this data? Apparently, rotate to this angle, it is not the best way because all the data points are mixed together, right? And when we rotate the data, okay, in this, for example, in this way, okay, originally it is a three-dimensional data, right? But after we rotation, we can draw this rotation. We can project the data in a two-dimension no space, right? So if I rotate it in this way, okay? So take a look at this mouse, okay? That will be the new X asset, and that will be the new Y asset, right? Okay, let's go back to here. So if we rotate the data in certain way, okay, and that will be the new X axis, that will be the new Y axis, okay? Original we have X, Y, and Z, right? If we can perform PCA and it becomes X prime and Y prime, if we can do such kind of thing, that is dimension reduction, right? And we hope, okay, we hope after the rotation, we can observe the data better. So what is the best rotation? Okay, and so let's take a look at the equation right here. Okay, in this example, okay, we have 4 dimension in the original space, okay, and we have n data points, okay, so we can calculate the variance of w, x, and y, and z. We have 4 dimensions, right? So think about one thing. If you move all of your data to, take this example, to the so I think if you rotate the data, there should be a center right here, okay? When you rotate the data, every data point rotate around the center point, okay? So if you rotate the data against the center point, okay, since you simply just rotate the data, okay, the distance between each data point do not change, okay, because every data point rotate together. So when you rotate the data, the distance between each pair of the data points does not change. And if all the relationship is still the same, which means that all the distance still not changes, okay, when you rotate the data, the variance, the sum of the variance will not change. And how do we describe rotation in a space? So that is, think about one thing, okay. I'm not sure in your high school, okay. I'm not sure if you knows that, okay. If we have a data point P1 and P2, okay, it has corresponding x1 value and s2 value, okay. So for P1, okay, you can simply just project the P1, rotate it, okay, with theta degree, and this P1 will be moved to here, that's P1 prime, and correspondingly P2 will be moved to P2 prime. Okay, you simply just rotate, or you can say that we can say that you simply just rotate the axis with theta degree. So after that, okay, if you do such kind of rotation, the P1 prime, the coordinate of P1 prime would be something like that. X1 prime, X2 prime would be cosine theta, sine theta, cosine theta minus sine theta. So that would be x1 cosine theta plus x2 sine theta. x1 cosine theta minus x2 sine theta. Okay, it really doesn't matter the value we write here, because it just mathematics tell us how to map the data from x1 x2 to x1 prime x2 prime. So as you can see that here we have a coefficient matrix right here, and we use this coefficient matrix, okay, with the original coordinate, and we can calculate what is the new coordinate after we rotate the axis with theta degree. Okay, so it's very similar right here. If we rotate the data, okay, and we will have rotation, so that would be something like that. If we use the original coordinate, that is a data point in the original space, right? And we times it with matrix, and it will become a new, it will become the data point in the new coordinate. So, but right here, the coordinate is PC1, PC2, PC3, PC4. Okay, we'll explain why we use this word later. Okay, so that is very simple. How do you rotate your data in a space? We simply just times something right here. Okay, and there's a very important thing that since you simply just rotate and all the distance, you have to you have to notice that originally we have four dimension, but in the new space we have 4-dimensional. It's 4-dimensional as well. Okay, we simply just rotate it, okay, to new axis. Okay, since we only rotate the data, so mathematics tells us that the variance before rotation and after rotation, the sum of the variance should be the same. They should be the same, because all the distance is still the same. We just simply redistribute the variance from the original axis, which is wx and yz, to new axis, PC1 to PC4. Okay, again, take a look at this one. When we rotate the data, for example, that is the original x and y and z, and you can project the data to x-axis, y-axis, and z-axis to calculate the corresponding variance on each axis. Okay, when we rotate the data like this, we have a new axis, new x, prime, y prime, and z prime. And again, you project the data to new axis and calculate the corresponding variance on new axis, and you will find out the sum of the variance will be the same. Okay, you can mathematically prove that. Okay, and that is a rotation. But what kind of rotation we prefer? Okay, as we can see that if there's a new exit, something like this one, then visually, okay, visually, we prefer this new exit. That is because the data point on the new exit looks it seems like they are not overlapped, right? No matter on the new exit or new x exit or new y exit, maybe it's like this one. And you can see that this data point spread widely in the new plane, right? So we can distinguish the data point of different classes. Take the iris, for example. So that is the new axis we prefer. Okay. So again, how do we find such kind of new axis? And so it really depends on how we find the new axis. Okay, based on the n data. So that would be the matrix we have to find. And because we don't have much time to talk about this, so I will give you a small example right here. So if you're interested in how to find those the best rotation angle to have the best new exit, so you may take a look at this one. In short, okay, we use eigenvalue and eigenvector to find the corresponding new exit. Okay, the direction of the eigenvector is exactly the new exit we like to find. Okay, and we can use the eigenvalue, okay, to have this very important property. Okay, this one. We can arrange that the variance of the new exit will be the largest one, and so on and so forth, so on and so forth. So in this case, since PC1, okay, we remove this one, okay. Since PC1 has largest variance, and we believe PC1 would be more important than PC2 because more variance means the data will be spread out on the new PC1 exit. So we deliberately arrange the exit, okay, by using their variance. So original we have dimension 4. So let's use a example, okay? So for example, original variance of W will be 15, 25, 40, 20. After principal component analysis, the PC1, the variance of PC1 will be the highest one, and the variance will be redistributed to the new exit. So maybe that is 65, 25, 9, and 1. Okay, so after we distribute the variance to the new exit, Okay, and we can manually set the value. For example, k equals 3 and k less than d. That means we can only use 3 new features, which is PC1 to PC3, to represent the original n data points. Okay, we can discard the new principal component, which has very low variance value. Okay, and as you can see, that some of these values will be 100 and this one will be 99. So that means we preserve 99% of the variance in the new 3 principal component exit. Okay, so it's really depend. So after we perform principal PCA, it really depend on you. How did you choose how many new exit you want to use, and what is the sum of the variance preserved? And most of the time we will preserve about for example 90% or 80% of the variance. So that is how we use principal component to preserve the data and to perform dimension reduction. Okay, so if you are interested in how the mathematics works, you can take a look at this example. Okay, and of course you can use sklearn to perform PCA, so we can plot the PCA. So I think it would be better to use Orange to present dimension reduction. Okay, so it is Iris. Okay, we have 4 features. So let's take a look at the unsupervised. Here is the principal component analysis right here. You simply just connect it to the PCA. So the configuration of PCA, you can see that here is the number of components we like to use. At the first place, you can simply just use the entire dimension. Okay, you can click. Okay, if we use only 3 components and it says okay, 3 component has 99% of variance. If we use only 2 dimensions to represent the Iris data, the total variance would be 95%. And if we use only 1 dimension, which is principal 1, then the expanded variance would be 72%. Okay, we use 4 right here because we would like to show you something. So right here, and you can click this one and it says, okay, we have the original data, 4 different length and width, right? So here is the result of the principal component. So that would be the new coordinate value of this data point in new exit system. And the principal one has 72% of the variance and the 23% and the additional 3% and the rest of them. And you can see that we arrange it by using this value, and we can see that's the principal component has very small variance. Okay, so simply so we can discard PC3 and PC4, for example. So we can simply just use 95% of the variance, preserve 95% of the variance, and the component becomes 2. And we can draw value right here, visualize right here, and we only use we only use PC1 and PC2 to draw the. So right here you can select of course you can use the original dimension to draw the figure, but also you can use PC1 and PC2 to draw the figure. So that is the best angle to observe the data if you use only 2 dimension, 2 principal component. Okay, so and again you can Sometimes you can use the dimension reduction data to perform um, prediction or testing. That is because sometimes we have too many features. So let's try. For example, logistic regression. Okay. So right here, you have to specify which feature you would like to use. So let's try this one. Okay, let's select column. So in this case, we simply just use PC1 and PC2 as the feature, and the target is iris. Okay, so take a look at this one. Okay, so for linear regression, oops, sorry, the data should be like this. Okay, so for linear regression, if you only use two-dimensional data, which is output by the PC principal component, the accuracy would be 92% right here, right? Would be 92%. But if you use the for example, if you use the original data right here, okay, and you can see that the actual classification rate is higher, is 97%. That is because when you perform principal component analysis, some variants are missing, right? So that means you for some data point you cannot distinguish them using a new exit. 5% of the variance is missing. So for classification purpose, the classification accuracy would decrease, would become smaller. That is because the information in principal component is not that accurate. 5% of the variance are missing. Okay, so be aware of that. But sometimes when you perform principal component analysis, okay, sometimes it removes some little noises, and such kind of noises would affect the classification accuracy. So sometimes when you perform PCA, it may slightly increase your accuracy. That is because you remove some not important variance, and those data would make this classification even better if you remove a very very small variance. But as you can see, for iris data set, even if you have 3 component, okay, the accuracy is not as high as you use all 4 original features. But in some data set, if you perform PCA and discard a little bit variance, the classification rate might be higher. So that is just an experience of my past, just some experience to share with you. Okay, so that is the dimension reduction. Okay, so we stop right here.